Thanks for the reminder.
Mhm.
All right, so hi everybody. This is April 23rd. We are in pre-calculus, and so today we're going to jump into chapter 8. But before we do that, what I want to do is talk a little bit about sort of what we've gone through this semester, and now how we're going to be kind of looping back to some of the things that we've seen before. Okay, so when we started this course, we started talking about functions in general, what they are, what do we use them for, and some of the notation. And then the very next thing that we did is we started talking about linear and quadratic functions, right? So we had linear functions that had this form y equals mx plus b, and then we had quadratic functions which, they had this extra term in there. They were a squared term, so it was like building up on linear functions, but then we added a squaring term in there. And once we were done with these, we sort of took a detour, and we didn't really talk about those types of functions for a while. We talked about trigonometry, exponential functions, logarithms, more trigonometry. But what we're going to do in chapter 8 is we are going to loop back, and we're going to continue to build off of what we learned about linear functions and quadratic functions. Okay, and so this is something that we call a polynomial. So what we're going to do is we're going to start in section 8.1 here. And so a polynomial is something that looks like this form right here. Now, on its surface, I think it looks pretty scary, right? There's lots of letters, there's lots of numbers that are going on there. But what I want to do is work up some examples. So I'm going to jump over to the blackboard, and we're going to see how we can sort of build up this equation from linear functions, from quadratic functions, into this more general sense. Okay, so Nick, how do you feel about this? I mean, looking at this notation, does this make sense to you, or?
Not really.
Okay. So let's go ahead and let's build this up with some examples, and we'll see how we can make some sense out of those letters and numbers. Okay. All right. So to start out here, one type of function that we could have, right? So I'm going to call this, I'll call it f of x, right? So f of x could be just a constant, right? So we could have a function that was like f of x equals 1. Okay, so if we start out like really, really basic, this would be, hey, f of x equals 1. It's just a number. It's just a constant, so it doesn't change. It would just look like a horizontal line. So we looked at these a little bit. But then, like, if we build this up, we can look at another function that was said, I'm going to add an x term in here, and maybe I'll look at something like 2x plus 1. Right, so now instead of just a 1, what I have is I've added this another term in here that has an x in it. And we called this a linear function, right? And so the general form of a linear function was this mx plus b, right? So we said, hey, I have an m in here, that's my slope. I have a b, that's my y-intercept. And these letters here, this m is like a stand-in, right? It's in place of some number that's representing our slope, and b is standing in for some number that represents our y-intercept, something like this over here. Okay. And so instead of m and b, what I'm going to do is I'm going to replace those. Okay, I'm gonna match these up with their power on x. So I'm going to call this a1x. I'm going to call this a naught. Right. So instead of m and b, I'm just going to replace them with these new numbers. Now I'm going to pick a1 here because I'm going to think about this as the exponent over here on x is a 1. And then there's this sort of hidden x to the 0 here, right? So if I put an x to the 0 there, that would be the 0th power. It would just be 1. So we don't write that, but if you want to continue this analogy, you could think of it. That's why we're putting a 0 there. Okay, and so the more general form of a constant function would just be a 0. Okay, so if we build this up to another step, right? So if I have another h of x function, we could have like I could add in an x squared term, right? So I could have a 3x squared plus 2x plus 1. And this is a quadratic function. So quadratic functions, we said, generally had this form ax squared plus bx plus c, right? So we looked at this. This was our general form of a quadratic function where a, b, and c were standing in for numbers, right? Like 3, 2, and 1. Okay, so what we're going to do is, since we're trying to build this up more generally, we're going to replace this a, this b, and this c with these numbers, these kind of forms of numbers that we had up above, right? So we had a naught, we call this a naught, or like the a sub 0. A1 would go here with the first power, and so to continue this trend, what we're going to say is this is a2, this is a1, and this is a 0, right, or a naught. Okay, so up to this point, these are types of functions that we've studied. We've studied a constant function, we've studied a linear function, and we've studied a quadratic function, right? So we're building up these steps. So what would the next step be here? Any ideas, Nick?
Add a third, something to the third power or cube it.
Yeah, right. So we could have some number. We'll just say, let's call it 4, right? Doesn't have to be 4, but here 4x cubed plus, then we could have a 3x squared plus 2x plus 1, right? And so if I think about this again, the general form of this is going to be, well, I'm going to have some number that goes out in front of x cubed. I'm going to have some number that goes out in front of x squared. I have yet another number that goes out in front of x, and then I'm going to have my final constant term there. All right, so as we're building this up, this type of function, so anything that's built up that looks like this, is called a polynomial function. Okay, so this class of functions that we're dealing with here, these are polynomials. Okay, so all of these things we call polynomials. Right, so these are, it includes linear functions, it includes quadratic functions, and then we can go to cubic functions. And so more generally, what we have is we have any polynomial function is going to look something like this, right? So we're going to start, there's a constant term out here that doesn't have any x's multiplied by it. There's some number that goes in front of the x, right? And then there's some number that goes in front of the x squared, and then, we can continue this out, right? So we're going to keep going, and in general, what we have is we have, there's some number that goes in front of the term that has the nth power. Okay, so no matter how far we go out, we might stop at cubic, right? So this could be a 4th power, it could be a 5th power, and then we could go all the way down, right? So all we're doing is we're taking x to some integer power, 2, 3, 4, 5, 6, 7, 8, 9, 10, as high as we want to go. We're multiplying it by a coefficient. That's what we call these numbers right here. And then we're adding them all up. Okay, so this would be a class of functions that we call polynomials. Right? All of these things put together. And it's honestly the most common thing that we're going to see in calculus. You see lots of polynomials and exponential functions and logarithms. So this class, these are the building blocks for how we're going to look at situations and model them in calculus and see how they are changing. Okay, so if we jump back over to our notes here, we can see that as this is written out, what we have is, right, we have our coefficients here, numbers that are being multiplied by powers of x to the n, and we just add them all up. Okay, so Nick, I'm going to kick it over to you. How is this? Did this make sense, or we have some questions about it?
I think that makes sense.
Okay. So what we've got here, we've got four, right? So we've got four different polynomials, and I want you to sort of just take a look at them. Each one of these over here, F, G, H, and M, are four different polynomials. We can sort of see, we can make some observations about these. And so as I look at them, as I look at the first one, this is sort of just a classic quadratic function, right? That we would have seen previously, right? So we've seen quadratic functions before. So we've seen stuff that look like this, but this one's a little bit different. So like, what do you notice about this one?
It's got like higher powers than we've been working with.
Yeah, right. It's got a sixth power in there. That's sort of the highest power that's there. So one of the things that I'm wondering is, like, some of the numbers are missing. Like, why don't we have an x to the fifth, or like, why isn't there a number on the end?
Would that be because its coefficient is 0?
Yeah, right. So
Like,
exactly right. So anytime these numbers are missing, it would be a 0, right? So sometimes, like, we don't always have a constant term here. So we would call this one a constant term. It's just missing, right? So it would be like a +0. We just wouldn't write it. Similarly, like some of our numbers, that if we look over here at D, our larger x powers, there's no number that's written out in front of them, and that would be a 1, right? So we're familiar with that. Okay, so part of the web work, what we're going to be doing is we're going to be identifying the different pieces of a polynomial. And so there's 4 terms or 4 pieces of it that are generally important for us. Okay, so the degree of the polynomial is the largest power. So when we're talking about a second degree polynomial, that's a quadratic. And so whenever you see the largest term is a square term, this would be a second degree polynomial. And then similarly for g of x, we would have a 6th degree polynomial. So what do you think about C and D? What would you say the degrees of C and D are?
So C is a 199th power or a degree polynomial, and D is a 3rd degree.
Okay, so you picked out that this is the highest power. Right, so one of the things that trips students up is we often want to look at the polynomial and try to pick out just the first term. So just keep in mind that they're not always going to be written in decreasing order here. So you might have situations where some polynomials, the highest degree is somewhere else, right? So you still have to look at all of them. Okay. Okay, so once we've identified that, then the leading coefficient is often very interesting for us. It can help us define behavior for polynomials. And so that's the number that we call them coefficients that go along with that highest power. So going through A, B, C, D here, if we can identify our leading coefficients. So over here, the leading coefficient is 1. I find the 6th power, the leading coefficient here is 17. Again, C is sort of the tricky one here, where we want to go and we say, hey, this is the 199th power. The coefficient is -0.75. Okay, and then over here, our leading coefficient again would be 1. Okay, and so what we call our terms here, right? So this entire thing would be our leading term, right? So if I take the highest power of x along with its coefficient, that thing's called the leading term, right? So this is our leading term, this is our leading term, this is our leading term, and then this is our leading term. Okay, so often what we're going to be thinking about is, what happens when we plug in really, really big numbers, and these numbers are going to be the ones that are the most important in those types of questions. Okay, so Nick, I'm going to kick it back over to you. What about the constant term for each of these? Can you go through and tell me what the constant term is for A, B, C, and D?
So in A, it's -1. In B, it would be 0. In C, it's going to be 0. And in D, it's -12.
Yeah, right. So you can read them off. And then if they're missing, right, if there's no constant term, then we'll call it 0. Okay. So what I want to do, I'm going to give you a minute here, and I want you to think about this question, right? So one of the things that we can do is we can have sort of recognition of plugging in different values into polynomials gives us different information. Okay, so if I wanted some specific pieces of information from polynomials, plugging in different values gives me that information. So what I want you to do is go ahead and plug in 0 into each of these, plug in 1. Tell me what you get, and then let's see if we can characterize what information these two values give us when we plug them into polynomials.
It's just it's going to come out with the constant term.
Yeah, right. So why would that happen, right? So do you think that's true for any polynomial?
I think so, because whenever you plug in 0, that's going to get rid of all the x terms.
Yeah, right. So this term right here, I'm going to have 0 to some power, right, which is going to be 0. And that's going to be whatever this number is, as long as it's multiplied by 0, that will become 0, right? So I'm going to get 0, 0, anything with an x in it, it's going to be 0. And then the only thing that will be left over is our constant term. Right, so if you have like a really big polynomial, one of the cool tricks that you can do is if you want to know what that constant term is, evaluating the polynomial at 0 can often be very helpful, right? So when we're doing things on the computer, sometimes our polynomials can be pretty large, and so we're not going to be doing this work up by hand. But if I want to know what that constant term is, just asking the computer to evaluate it at 0 would, in fact, give me that constant term, right? So what we're going to see here in a little bit is, we aren't always able to figure out what the constant term is unless we have our polynomial in this form. But what we're going to see down here is, hey, if my polynomials are factored, it might not be so easy to figure out what those constant terms are. And so one of those cool tricks is plugging in 0, right? So that will always give you the constant term. All right, what about x equals 1? What did you notice?
I think it's just the coefficients. You add the coefficients together.
Yeah, right. So if you wanted to know what the sum of all the coefficients was, then that would be when you plug in 1. All right, so it will effectively eliminate your x terms because it's multiplying them by 1, right? So this would be your first coefficient times 1 plus your second coefficient times 1 plus all the way down, right? Yeah, so this is going to be the sum of the coefficients, and then this is going to be your constant term. So some interesting things here. Okay, so we've done this, right? So we've identified leading terms and constant terms and the different pieces of polynomials. So what we're going to do now is we're going to think about the factored form of polynomials. Now, we're not going to spend a whole lot of time trying to factor polynomials by hand, right? So what we'll see sort of at the end of this is we can use Desmos to really help us out in factoring these things. So if I have a polynomial that's not factored, Desmos is really going to be able to help me factor that polynomial. But one of the issues is trying to figure out how like a graph relates to the factored form. So we did this a little bit for quadratics, but we are going to do this now here. So what we're going to do, I have 4 polynomials in factored form, And we're going to practice expanding these out. So one of the things that we did for quadratic functions was we talked about foiling, right? So Nick, I think you remember foiling, right? So, and when we foiled, I sort of cautioned against that, right? I said, foiling is okay, but we want to be able to generalize this. Okay, so what I'm going to do, I'm going to write down our polynomial here, x minus 2 times x plus 3 times x plus 7. All right, and I'm going to jump over to our blackboard. So foiling does not help us when we have more than just two terms, right? So FOIL is this acronym that stands for first, outside, inside, last. And so it gives you sort of a mnemonic to remember how we multiply just two of these terms together. But now we've got three. So one of the things that I talked about earlier in the semester was this idea of an area model. So Nick, do you remember us talking about that back when we were in the classroom?
Mm-hmm.
And so is this something that resonated with you, or did you just stick with the foiling?
I mostly just stuck with the FOIL.
Okay, so what we're going to do then, I do want you to think about this area model, right? Because it's going to help us stay organized when we are expanding bigger polynomials. Okay, so as we're doing this workout, right? So I'll just remind us all what the area model is, right? So what we saw earlier in the semester is we made a little box like this, right? It was a rectangle, and in order to find the area of this rectangle, what we're going to do is we'd multiply, right? We'd multiply sort of the length by the width, right? And that would give us the area. Alternatively, what we could do is we could find the area of the four smaller rectangles and then add them together. And so this idea is going to help us out with multiplying these polynomials together. Okay, so what I'm going to think about is that I have sort of an length here, x minus 2, and then I have a length here, x, and then this is a plus 3. Okay, so this is an x minus 2, and this is an x plus 3. And what we're going to do is just multiply all these things together. Okay, so I would get x times x, this would be an x squared. We get x times 3, this is 3x. X times negative 2 is negative 2x. And then down here I get a minus 6. Right, so what I'm doing is I'm thinking, right, the length of the rectangle is x plus 3, the height is x minus 2. And so in order to find the area, I'm going to add up all of these together, right? So we would get, x squared, and then 3x minus 2x is plus x minus 6. And so what this tells me is now, if I bring this down, x minus 2 times x plus 3, this is x squared plus x minus 6. And I want to multiply all that by x plus 7. Right, so looking at this model here now, I want to take this. FOIL no longer really helps me, right? Because if I have I have this new middle term here, right? I have this new middle one. And so FOIL doesn't generalize, right? So our first terms, our last terms, we don't have anything for this, right? For this term.
Yeah.
So what we're going to do is I want you to think about this as another area model. Okay, so when I multiply these together, just to help us stay organized, right, we'll have, instead of a 2 by 2 rectangle, what we're going to do is we're going to have a 3 by 2 rectangle. So something like this. Right, so 3 by 2, because in one of these I have 1, 2, 3 terms, right? So I have 3 terms here and I have 2 terms here. So we'll have x squared, this would be a plus x minus 6, and then this would be an x, and then a plus 7. All right, so what I can do is, it's a visual way for me to see that this x has to get multiplied by all three of these terms, and the 7 has to get multiplied by all three of these terms. Okay, so as we go through here, it sort of breaks it down where I can now think about this. X times x squared is x cubed. This is x squared minus 6x, right? And then I'm going to get a 7x squared, 7x, and then minus 42. So adding all this together, what I should see is, right, so these two terms here, those are the same x squared, so those are going to get grouped together. And then these two terms here both have x's in them, so I'm going to group those together. Right, so the final result here is I should get x cubed, and then I should get plus 8x squared plus x, and then minus 42. Okay, so putting it all together, I want to recognize that x minus 2 times x plus 3 times x plus 7 should be the same, right? So these two expressions down here at the bottom, I just want to recognize, hey, these really are the same thing. Right, so what do you think? Did we make any mistakes?
No, that looks good.
Okay, so how would you verify this? You have like a way to verify? All right, so here's what I'm gonna do. Let's jump over to Desmos as usual and see how this can help us. And so here's our polynomial, x minus 2, x plus 3, x plus 7. Or you can see that it's a big polynomial here. Now I'm going to type in our expanded form. And what do we notice?
The same graph.
Yeah, right. So if I graph them, right, they should be the same thing, right? So it seems to me here that the blue is my expanded form, the red was my factored form, and they really are, right? They really are the same, right? So we can see that visually, this is a visual confirmation that my two functions are the same, right?
Now, if we were to plug in like 0 though into those equations, would that still give us the same the constant term for both of them?
It should, right? So these are really the same. So let's call them f and g. So if I ask Desmos what is f of 0 and what is g of 0, in both cases it gives me negative 42. Yeah.
So maybe that would be a way probably to do it like in your head or on paper.
Yeah, so if you had something like this and you wanted to identify the constant term.
Yeah, or even just to check that they're the same. But I mean, I guess you could theoretically have two different equations that had the same constant term though.
Right. So it would be, so we would call that it's a necessary condition. So they would necessarily have to agree on the constant term. But it wouldn't be sufficient to say that they are in fact the same. Yeah. But if they were different, then you would say, yeah, they're not the same. Okay, so this was sort of some algebra practice, right? So expanding these things out, and then here's a way to verify, right? So we can verify that our work is correct. Okay, so what I did is I worked through G here, and so Nick, I'm gonna give you a minute to think here, and I'll give the people at home on YouTube a minute to think as well. And so here, let's try this out with A, C, and D, right? So try out a couple of these, and we'll see how far we can get. Okay, have you been working on any of these in the last couple minutes, or? No,
I haven't.
Okay, so try out A, and then try out C, and then try out D, and we'll see how far we get.
Okay.
All right, so here we'll jump back in, and so this is my work for part C. Nick's thinking about his work as well, but while we're doing that, while we're sort of finishing up part D, I want to just point out one sort of helpful thing that we see a lot in polynomials, and if we're multiplying these things together, so if we go down the line, right? So you would sort of multiply these two, and then you'd multiply in this one, and then you'd multiply in this one. That's not always the most efficient way to go about these things. So oftentimes we want to identify patterns, and one of those patterns is sort of what we call the difference of squares, right? And so anytime that we have terms that look something like this, where we have an x minus 1 and x plus 1, they come together in a nice way when you multiply them out. So notice that when I multiply these two together, I get an x squared, and then this becomes a minus 1, and there's no middle term there, right? Those things end up canceling out. And this is really x squared minus 1 squared is the way to think about it. So we call this a difference of squares, just like this is x squared minus 2 squared, right? And it would factor out this way. So if I observe this, right, so if I look at my polynomial on the surface, and then instead of sort of just plugging everything in left to right, if I look at the structure, I'll notice that I have two differences of squares here. So I have an x minus 2, x plus 2, and I have an x minus 1, x plus 1. And so if I go ahead and multiply those separately, that actually produces something that's a lot nicer to multiply out. So then when I get down to my next step, I have something that looks like this, and I can multiply it all out in one area model. And so what we end up with here at the end is x to the 4th minus 5x squared plus 5. Right, so might be a little bit different. So Nick, I don't know how you did it. Did you do it the same way that I sort of illustrated here, or did you kind of go down the line?
I just went down the line.
And so when you did that, so you ended up probably doing a lot more multiplications?
Yeah.
Yeah, so this is one thing that, I put this one in my notes in particular just to sort of illustrate this. This is something that's very common that pops up that we see. So if you can recognize things like this, sometimes it makes your life easier.
Isn't that a plus 4 though? At the end, the last term.
Oh yeah, thank you.
Yep.
My mistake. So x squared minus x to the 4th minus 5x squared plus 4. Yeah, so so you see, even I am going to make some mistakes in there. So it's always good to go back and verify. Okay. Okay, Nick. So how did you do? Do you want to check in, or did you check your stuff on Desmos?
I did not check it on Desmos yet.
All right. So do you want to do that together?
Yeah.
You can read it off, and then I'll go ahead and put our stuff into Desmos. So we'll go through. So this one, I think we should feel pretty good about. Let's go ahead and check this one. X plus 1 cubed, x minus 2, x minus 1. All right, so you got x minus 2, x minus 1. And so you've got this sort of bumpy polynomial. So what did you get?
I got x to the 5th plus 6x to the 4th plus 14x to the 3rd plus 16x squared plus 9x plus 2, which is not the same thing.
Yeah. So what happened there?
I have no idea.
Yeah, so we made some mistake along the way. This is okay though. So when I look at this at the start, some of the things that I pick out is your constant term correct? Right. So can you verify quickly? Is your constant term correct here?
I'm not sure.
So remember what we talked about before, right? So for plugging in 0, right? So if I were to plug in 0 here for all these x's, and if I plugged in 0 for all these x's, and multiplied it out, would we get positive 2?
No. Wait. Yes, we would.
We would, right? Yeah. So this is right. So whatever happened here, this ended up being correct. So we can verify that. So your leading term, would you definitely have an x to the 5th? So one way to think about this is as you go through, right, this is going to contribute 1x. This is going to contribute 1x. And this is going to contribute 3 x's, right? So it's going to be an x cubed in there. So you're going to end up having a total of 5 x's at most being multiplied together. And so you should have an x to the 5th out there. So just at the front of this, I can verify without even multiplying everything out that this term x to the 5th is correct. And that this term plus 2 is also correct. Okay. So were you using the area model along the way, or did
yes.
All right, so let's go ahead and jump over and let's see if as I go along, if we can sort of see what happened here. Now, for everybody at home, this is good algebra practice, right? So one of the things we're doing in pre-calculus is we're sort of brushing up our skills. So this is a good practice for us to think about, expanding terms and doing some algebraic manipulations. It's a good exercise to go through. All right, so if I'm thinking about this and I want to multiply these together, the first thing I'm going to notice again is I have this x plus 1 and I have an x minus 1 in there. So what I'm going to try to do is I'm gonna bring 2 of these together, right? So I'm gonna view this as x plus 1 squared times x minus 2. I'm going to pull one of those x plus 1s over here, right? So I'm going to end up having to multiply a bunch of things together anyways. But if I rewrite it like this, then I can think about, I have an x minus 1 and an x plus 1. So right away, I'm going to rewrite this as x plus 1 squared times x minus 2. And then these 2 multiplied together will be x squared minus 1. So how does that look to you, Nick? Does that make sense, or?
Yeah, that makes sense.
Okay, so first, for me, this is the way that I'm going to work through it. It says, think about it this way. I think this is going to end up making my life a little bit easier. Right, so from here, what we can do is we could start thinking about multiplying things together. And so maybe we want to look at this as 2 different pieces, right? So I'll look at it as this red piece, and then maybe I'll look at it as the yellow piece, right? If we wanted to think about it that way. Right, so these are both going to be the area models that I get, right? So in the yellow, we'll do a quick area model here to multiply these together. So you get an x squared minus 1 along the top and an x minus 2 down here. So this is x cubed minus x minus 2x squared plus 2. x cubed minus 2x squared minus x plus 2. Hey, where are you going? Chocolate hands? Hey, come here. Let me see you. Ugh. Sorry about this.
No problem.
All right, so is this good so far? X cubed minus 2x squared minus x plus 2?
Yep.
And down here, we're going to get this x plus 1, right? So we'll get an x plus 1 along the top, and we'll get an x plus 1 on the side. So we get x squared plus x plus x plus 1. And so this becomes x squared plus 2x plus 1. Okay, so I'm breaking this off into two pieces. And as a problem-solving strategy, one of the things I'm doing here is I'm taking this sort of big problem that I can't do in sort of one step, and I'm breaking it down into smaller, more manageable pieces, right? So now this yellow, right? So if we're sort of just tracking the colors here, I'm really multiplying the red stuff times the yellow stuff, right? Right, so when this comes back together, we're going to end up multiplying these two together, which, so let's bring this over here, okay? And so really this is going to end up being, we're going to have an x squared plus 2x plus 1 times x cubed minus 2x squared minus x plus 2. So in your work, did you have anything that was like this, or?
Not quite. Mine was a little different.
All right. So as I'm moving along here, as you're double checking me, does this all seems pretty reasonable?
Yeah.
Okay. So now, if I'm going to expand this term right here, if I'm going to expand all this out, for me, without doing it as the area model, right, you'd be like drawing a bunch of arrows to everything, and things would get pretty messy. I think the area model helps keep us organized. So what we're going to need here is we're going to need a 3x4. Like this, right? So we're going to have over here x squared plus 2x and then a plus 1, and we would have an x cubed minus 2x squared minus x plus 2. Right, so something like this. And at least for me, this sort of grid helps keep me organized. And then I can see right away. So some things that we picked up on before, our leading term is going to be x to the 5th, right? That's going to be these two boxes multiplied together. My constant term over here is going to be a plus 2. And we just have to figure out sort of all the stuff that we have going on in the insides, right? So we'll go through and multiply this together, right? So we get, this is minus 2x to the 4th. This would be minus x cubed, and this would be plus 2x squared. Right, so here we get 2x to the 4th, and then we would get minus 4x cubed minus 2x squared. This is plus 4x. We get x cubed here, and then minus 2x squared. This would be minus x. Okay, so one of the nice things here is if we see, right, so we have our terms are sort of grouped on these diagonals, right? So all of my x cubes are here, all of my x squareds are here, all of my x's are here, right? So as I go around, right, so we're going to come down and we can see that everything is sort of organized pretty nicely, right? So in the end, what I should get is I should have an x to the 5th. And then if we think about our x to the 4ths, what happens here, it looks like we don't have any, right? It looks like they cancel. You get a plus 2 and a minus 2.
Yep.
And then for our cubes, we're going to have, it looks like we're going to have a minus 4x cubed. And then it looks like a minus 2x squared. And then plus 3x, and then plus 2. Okay. So let's go ahead and, right, so we should verify this. So if you're doing this at home, right, so I'll go ahead and type it into Desmos as well. Then we can double check here. Right, and so again, I'll share my screen. So here we have it, right? X to the 5th minus 4x cubed minus 2x squared plus 3x plus 2, right? And then it is all multiplied out. And visually, we get that confirmation that this is what we want.
Mm-hmm.
Okay, so without seeing exactly what you did, Nick, it's hard for me to say where it went wrong, but did this thought process that I went through help you out?
Yeah, I figured out. I just forgot to put a minus sign in my big box. I forgot to drag it over.
Yeah, and so just that one tiny little error can cause lots of things down the line, right?
Yeah.
So what I would encourage, right, you and everybody else at home, think about this not only just as an exercise. Certainly, it's an exercise in algebraic manipulation, but also in problem-solving strategy. So specifically, we can see visually right here. What I did is I took sort of one big problem and I broke it down into two smaller pieces, right? So instead of just sort of going right down the line and sort of chunking away at this, I tried to take a more efficient approach by breaking it down into two different problems that I can do more efficiently, right? So don't try to just take it one big problem at a time. Break it up into smaller pieces and deal with those pieces individually. So throughout calculus, throughout mathematics, and life, I guess, that's a really good strategy. So if you have a tough problem to tackle, try breaking it up into smaller, more manageable pieces to make some progress along the way, and then put all those smaller pieces together in the end. And so in both mathematics and life here. Okay, so with that, let's go ahead and see what else we got. And so here's our Desmos window. We'll leave that up. So I asked you all this question down at the bottom. I say, when I'm looking at these polynomials, when I look at stuff like this, factored forms are often very helpful, right? So if I look at this factored form, there's certain pieces of information that I can get right away from this. And so some things that might be interesting to us are the zeros. Okay, so have you put this together, Nick? How these factors relate to the zeros of our polynomials?
No.
Okay, so let's see these factors. Right, we're going to jump back over to Desmos. And so if I look at my factored form here, I'm going to go ahead and then I'm going to click on my zeros, and we're going to see sort of what those numbers are. So how do these numbers, 2, 1, and -1, relate to these numbers over here?
They're being subtracted from the x's.
Yeah, right. So this 0 right here, 2, 0, goes along with this factor, right? So if I plug in 2, it's going to make this term equal to 0, right? And so I'm going to get 2 minus 2, so that would give me an output of 0. Okay, and then this 0 right here, 1, goes along with this one, and -1 goes along with this one. Okay. So if we go back to our notes, right, like what are the zeros of this?
So it'd be 1, 2, and 0.
Yeah, 1, 2, 0. Right. So if I were to graph this, x times x minus 1 times x minus 2, what I should see, right, so if we get rid of this, x times x minus 1 times x minus 2, we should notice that, hey, right, the 3 points where it crosses the x-axis are 0, 1, and 2. And so coming over here, you should see that it's, so what are the zeros on these?
2, -3, and -7.
Yeah, right, so plugging in 2 would give you here, here, and here. So what this does is it gives us a nice theorem, and that we call the factor theorem. We said any real number c, right, so it doesn't matter what the number is, that's going to produce a 0 in your polynomial if and only if you can factor an x minus c out of there, right? So if you have any polynomial, if you can identify a 0, we should be able to factor out the corresponding term, right? So if 2 is a 0, then we should be able to factor out an x minus 2 along the way, right? So let's take a moment and let's think about this, right? Do we have some zeros here? So how could I verify that if I plug in 0, the number 0, it's going to give me a place where I cross the x-axis? Right, so what should you see when you plug in 0 here?
The equation should equal 0, or yeah, it should equal 0.
Yeah, right. So you plug in 0, you're going to get 0 minus 0 plus 0 is 0, right?
Yeah.
So what we should be able to do here when I look at this equation is I should be able to factor out sort of an x minus 0, or just factor out an x out of this. Okay, so if we think about it this way, right? So this would become x times x to the 4th minus x squared plus 1. Right, so the fact that, I can identify one of the zeros tells me that I should be able to factor out that corresponding term there. Okay? And so similarly, we can do similar things with these, right? So if I want to know that 3 is one of the zeros, right, to this one, but I can plug in 3, I'm gonna get here 27 minus 2 times 9 is 18. Minus 15, and then plus 6, right? So if I add all those up, 27, right? So you're going to get 27 plus 6 is 33, minus 33 is 0. And so what I should be able to see is that for this p of x right here, it's going to be able to be written as x minus 3 times something that I'm not sure about yet, right? It's going to be x minus 3 times. What I do know is it's probably going to be a quadratic, right? So there's going to be an x squared term in here somewhere. But beyond that, I'm not sure what would go in this spot, right? So what the factor theorem is telling me is one of the factors will be x minus 3. The rest I'm not sure, right? But if I could figure out what the other zeros are, then I should be able to factor some of those things. Okay, so how do you feel about this so far?
That makes sense.
Yeah, so kind of like quadratics, right? If we could find the zeros on the graph, then we were able to factor our quadratics, right?
Yeah.
So now what we can do something similar with polynomials here. Okay. So what we can do is we can look at these, and I'll ask questions like, hey, what are the solutions to this polynomial equation? Okay, so let's try a couple of these out together before we're out of time here. Right, so I'll copy down the first two, and then we can think through them together. Okay, we'll jump over to the blackboard. Okay, so if I wanted to solve these, effectively what it amounts to is me trying to factor them. So what do you think?
The first one we can pull an x out.
Yeah, we'll pull an x out of this, right? So you get x times x squared minus 1 equals 0.
Yep.
And then what?
And then when we know one of them is going to be 0.
Right, and then can you factor this term?
Let's see. We could take the square root of both of them.
You could. Remember what we were talking about before with that difference of squares, though?
Oh, yeah. So is it x minus 1, x plus 1?
Yeah, right. So this is one of those situations where we're going to see that again, right? So it's a difference of squares, and so it will factor like this. And so writing it out in the factored form, what this tells me is that my solutions here are x equals 0, x equals -1, and x equals +1. And those come from, right, this gives us x equals 0. This one gives us x equals -1. And then this one gives us x equals +1. Okay. So what about this one down here?
So we could pull an x out.
Yeah, again, we'll pull an x out of this. Get x squared plus 2x minus 15.
And then the x squared plus 2x minus 15 should factor to an x plus 5, x minus 5. Or not minus 5, minus 3.
Mm-hmm. Yeah, x plus 5, x minus 3, right? So what are the solutions?
Well, isn't that x being multiplied by both of those? Oh, wait, no, never mind. There already is.
It is, yeah. So the multiplication all happens in one big group, yeah.
Yeah. So then the factors are going to be 0, -5, and 3.
Yeah, right. So we'll have our solutions would be x equals 0, x equals -5 comes from here, and then x equals +3 comes from here. Yeah. Yep. And so sometimes, right? So again, we haven't talked about sort of factoring our polynomials completely in general, and we're not going to spend a whole lot of time on that. We'll see. We can do it in Desmos, but yeah, I mean, if we have something that's quick, if we have certain things that are like give us a quick way to factor, or some things that are quadratics that factor nicely, sometimes it's easier just to do them out by hand. Right? And so in our last minute here, we'll probably, a lot of the time we're going to see things like this, or we'll be able to use Desmos where we're either given the factored form, right, or we're given something where we can factor it relatively quickly. Okay, so this should give you a pretty good start on the web work that's due. I don't think it's due till the end of next week, but what we'll do next week is we're going to start thinking about, how could we now start to create our own polynomials. Okay, so if I give you some information, like if I tell you what the zeros are, can you create a polynomial with those zeros? And is that enough information for you to determine the polynomial exactly? Like if I give you these 3 zeros here, 1, 2, and -3, well, how many different polynomials are there that have those zeros? Is there only one? Are there multiples? And so we'll work through this and how, if we're given a graph, how we might be able to determine the equation of a polynomial and then use Desmos to actually factor. So some of these things down here are pretty messy, but using Desmos, it actually is not that bad to factor them. But yeah, we'll pick up So on Tuesday, we'll pick up here where we can start creating our own polynomials, factoring them with the aid of Desmos. Okay, so Nick, you have any last questions before we sign off for the weekend?
No, I don't think so. Thank you.
You're welcome. Hope things are good for you and your family. Have a great weekend.
Thanks. You too. Bye.